Okay, next we're going to talk about how to sort some data in a collection. Whether that collection is an array or a vector doesn't matter. The algorithms are the same. Okay, so imagine someone gave you a set of index cards with a bunch of numbers on them, perhaps these numbers. Okay, and they asked you to sort them. Okay, well, what you would probably do is you would probably do something like this, where you would select the first card, which is 14 here, and then you would move all the other cards around it. So cards less than or equal to 14 would move to the left of 14, and cards greater than 14 would move to the right. Right, so you would just kind of start going through here. 20, that's greater than 14, so that's going to end up on the right. 9 is less than 14, it's going to end up on the left. 16 is greater, it's going to end up on the right. 7 and 12 are less than, so they're going to end up to the left here. So the numbers that are less than 14, 9, 7, 12, they're over here on the left. The numbers that are greater than 14, 20, and 16, they end up on the right. Okay, notice that the card with the 14 is in its final sorted position. Right, so if we're to look at the actual cards in sorted position, they would look something like this. Okay. And after you move those cards around here, we'll see that, yeah, the 14 really is in its final sorted position. This is not true of all the other cards, so these ones aren't in their final sorted position. Turns out the 12 just coincidentally happened to land in its final sorted position, but that was more of a coincidence. So what you would probably do next, of course, after doing this one time, this is not the final sorted order. So what you would probably do is repeat the process, this time starting with 9 and moving the cards around it until you got to the 14. Because you know none of the cards after the 14 will come before the 9. And you would probably do this repeatedly until all the cards were sorted. Now we could mimic this solution in code. It's called the quicksort algorithm. But it uses some advanced features like recursion that we're going to talk about in later courses. Since we don't want to talk about recursion right now, we're going to have to find another way to sort a collection of values. And a simpler solution is to use an algorithm called bubble sort. So bubble sort looks at adjacent pairs of items and then always moves the larger of the two numbers to the right. Okay, so what do I mean by adjacent pairs? Well, let's go back to our original set of numbers. Adjacent pairs are just two numbers that are right next to each other. So here we have 6 numbers. There are actually 5 adjacent pairs. 14 and 20, 20 and 9, 9 and 16, 16 and 7, and 7 and 12. Okay, adjacent just means, numbers that are right next to each other. Okay, so basically what we're going to do is we're going to look at each left-hand value and compare it with the right-hand value. We're going to do this for each adjacent pair. And if the left value is less than or equal to the right value, we're not going to do anything. We're just going to move on to the next adjacent pair. So for example, in the first adjacent pair, we have 14 and 20. 14 happens to be less than 20, so we're not going to do anything special. Okay, we're just going to move on to the next adjacent pair. However, if the left value is greater than the value on the right, we need to swap the two. So in this next adjacent pair, the left is 20 and the right is 9. 20 happens to be greater than 9, so we're going to swap these two. Okay. So we're not going to have a 20 there anymore, and we're not going to have a 9 any there. Okay, they get swapped. Okay, this has the effect of always moving the larger of the two numbers in the adjacent pair to the right. And if you do this for every single adjacent pair, it has the effect of moving the largest number to the far right. Okay, so let me prove that to you. Let's go through here and just look at each adjacent pair and apply this algorithm. Is 14 greater than 20? No. So we're going to move on. Is 20 greater than 9? Yes. So we're going to swap those. Okay, the next adjacent pair is 20 greater than 16? Yes. We're going to swap those. Is 20 greater than 7? Yes. We're going to swap those. And is 20 greater than 12? Yes. We're going to swap those. Okay. So what happens is the largest number bubbles to the end of the collection. Okay, that's where the name bubble sort comes from. So the 20, which was over here, got pushed or bubbled to the end. Okay, so how are we going to do this in code? Well, assuming we have a vector of items here, we're going to want to go through all the items and do a comparison of left versus right. Now in this case, my counter j, j is always going to represent the item on the left, and then j plus 1 will always be the item right next to it to the right. Okay, because we're going to be using j plus 1 inside some square brackets, we want to make sure that we don't go quite to the end inside this for loop. So j, we want to stop 1 short of the final position because we're going to add 1 to that value at the very end. Okay, so basically if vec at position j is greater than vec at position j plus 1, we know we have to swap the elements. Okay. If this is not true, we don't really have to do anything. We're just going to move on to the next pair and continue to go through the adjacent pairs. Okay, so let's talk about swapping for a second. Swapping is actually a 3-step process. Okay, so let's say I had 2 variables in memory, x and y, and I wanted to swap them. Well, I can't just put 20, the value inside y, inside x, right? Because if I just put 20 inside here, I'm going to lose my value of 10. So swapping always requires that we create a kind of a temporary holder, where the first thing we're going to do is we're going to make a copy of one of the values inside your temp variable. Then we could write over this value 10 with the value of 20. And then finally we're going to take that temp value and write over the original 20 with 10. Okay, so we've swapped these 2 values. It required this third piece of data. And that's exactly what's happening inside this loop here. We just have temp, which is going to hold one of the values, vec at position j. Then we immediately write over vec at position j with the other one, vec at j plus 1. And then lastly, we say vec at j plus 1 is equal to the temp value. Okay, so it turns out that moving through all of the adjacent pairs places one item in its final sorted position. Right? The 20 got placed in its final sorted position. Now, if we do this again, right, so here's the vector now with the 20 where it's supposed to be. If we do this again, the next largest number is going to be in its final sorted position. So let's do the exact same thing, just starting at the beginning again. Is 14 greater than 9? Well, that's true, so we're going to swap these. Is 14 greater than 16? No, so we won't do anything. We'll just move on. Is 16 greater than 7? Yes, we're going to swap those. Is 16 greater than 12? Yes, we're going to swap those. Is 16 greater than 20? No, so we won't do anything, and we've gotten to the end. So now the next largest number, 16, is in its final sorted position as well. Now every single time we do this, every single time we go through each set of adjacent pairs, one more number gets sorted. And there's another way to think about this, is to imagine, really there are 2 parts of the collection, an unsorted part and a sorted part. Okay. So the very first time Right? Before we did any work with this vector, it was just kind of all unsorted. Right? And then we did one iteration where the value 20 got pushed to its final sorted position. Then we could kind of think of this collection as being in two parts. Here's the sorted part, the 20 is here, and all the other numbers are over here. But then we do the bubble sort again, and what happens is the 16 gets pushed to its final sorted position. And then all the other numbers here, these are more or less unsorted. So we do this again, and of course what's going to happen now is the 14 is going to get pushed to its final sorted position. And so on, and so on. And if we do this, let's see, 1, 2, 3, 4, 5 times. Actually, if we do it the last time, this by definition is kind of sorted already, but if you want to do it one extra time, that's fine. So with 6 elements, it took 6 full iterations of doing that inner loop, and look what happened. We have a totally sorted collection down at the bottom. So going through the adjacent pairs always moves at least one element from the unsorted part to the sorted part. And since one time through the loop we'll place one of the n items in order, we need to do this about n times to fully sort the collection of values. Okay, so we can update our code a little bit. This was basically pushing one item to its final sorted position. If we wrap that inside a loop that goes about n times, remember the vector knows its own size. Okay. This is essentially exactly the same as what we did a second ago. What should happen now is, n times we're going to bubble one item to put it in its final sorted position, and at the end of this nested for loop, all the items should be totally sorted. Now this code can be put inside a function that can be reused anytime you need a sorted collection. So you might have a sort function that takes a vector by reference, and you could have that little nested for inside here. And that function will basically work anytime you need to sort some values. So oftentimes we're going to want to measure how much work is required for an algorithm. In this case, there are n items in the collection. It takes about n iterations of the inner loop to sort just one item. However, if we do this n times, we find out that all of the items will be sorted. Therefore, we can say the amount of work required to sort n items really is a function of n. In particular, it takes about n squared iterations of the inner loop to sort a collection. Now, in later classes, we're going to talk more about measuring work that the computer has to do. When we do, we're going to learn that the quicksort, the algorithm I mentioned earlier, is called an n log n algorithm. So when n is large, quicksort is much, much more efficient than bubble sort. However, bubble sort works just fine if n is relatively small, and it also has the benefit that it's relatively simple. Quicksort is going to be quite a bit more complex to write the code to perform quicksort. One last note, remember that strings can be compared just like numbers. So we can sort a collection of words just like we sorted the numbers in this example. Okay, so for now, bubble sort will suffice whenever we need to sort a collection of values.